Subset selection. In subset selection, we are interested in finding the best subset of the set of features. The best subset contains the least number of dimensions that most contributed to accuracy. We discussed the remaining unimportant dimensions. Using a suitable error function, this can be used in both regression and classification problems. There are 2 to the d possible subsets of d variables, but we cannot test for all of them unless d is small, and we employ heuristics to get a reasonable, but not optimal solution in reasonable polynomial time. There are 2 approaches. In a forward selection, we start with no variables and add them one by one, at each step adding the one that decreases the error the most, until any further addition does not decrease the error, or decreases it only slightly. In backward selection, we start with all variables and remove them one by one, at each step removing the one that decreases the error the most, or increases it only slightly, until any further removal increases the error significantly. In either case, checking the error should be done on a validation set distinct from the training set, because we want to test the generalization accuracy. With more features, generally we have lower training error, but not necessarily lower validation error. Let us denote by f a feature set of input dimensions, xi, I starting from 1, 2, 3 until d. E of f denotes the error incurred on the validation sample, when only the inputs in f are used. Depending on the application, the error is either the mean square error or misclassification error. In a sequential forward selection, we start with no features, f equals to empty set. At each step, for all possible xi, we train our model on the training set and calculate E of f union xi on the validation set. Then we choose that input xj that causes the least error, that is, j equals to argument minima of the E of f union xi, where the minima is taken almost all possible I, and we do the following. We add xj to f if the error of f union xj is less than error of f. We stop if adding any feature does not decrease E. We may even decide to stop earlier if the decrease in error is too small, where there is a user-defined threshold that depends on the application constraints, trading off the importance of error and complexity. Adding another feature introduces the cost of serving the feature, as well as making the classifier's regressor more complex. This process may be costly because to decrease the dimensions from d to k, we need to train and test the system d plus d minus 1 plus d minus 2 and so on plus d minus k times which is big O of d squared. This is a local search procedure and does not guarantee finding the optimal subset, namely the minimal subset causing the smallest error. For example, xi and xj by themselves may not be good, but together may decrease the error a lot, but because this algorithm is greedy and adds attributes one by one, it may not be able to detect this. It is possible to generalize and add multiple features at a time instead of a single one at the expense of more computation. We can also backtrack and check which previously added feature can be removed after a current addition, thereby increasing the search space, but thus increases complexity. In floating search methods, Pudio, Novovikova, and Kittler 1994, the number of added features and removed features can also change at each step. In a sequential backward selection, we start with f containing all features and do a similar process except that we remove one attribute from f as opposed to adding to it, and we remove the one that causes the least error. That is, we select j equals to argument mean of the error of f minus xi, where I is chosen among all possible mean, and we remove xj from f if the error of f minus xj is less than error of f. We stop if removing a feature does not decrease the error. To decrease complexity, We may decide to remove a feature of its removal causes only a slight increase in error. All the variants possible for forward search are also possible for backward search. The complexity of backward search has the same order of complexity as forward search, except that training a system with more features is more costly than training a system with fewer features, and a forward search may be preferable, especially if we expected many useless features. Subset selection is supervised in that outputs are used by the regressor or classifier to calculate the error, but it can be used with any regression or classification method. In the particular case of multivariate normals for classification, remember that if the original d-dimensional class densities are multivariate normal, then any subset is also multivariate normal, and the parametric classification can still be used with the advantage of k by k covariance matrices instead of d by d. In an application like face recognition, feature selection is not a good method for dimensionality reduction because individual pixels by themselves do not carry much discriminative information. It is the combination of values of several pixels together that carry information about the face identity. This is done by feature extraction methods that we discuss next.